So now that we know how to calculate the torque generated by an individual force about some pivot, what we want to do now is talk about how we can talk about the net torque generated by a series of forces about that pivot. The net torque, like the net force, is just a vector addition problem. The nice thing for us, because we're going to deal with forces and position vectors that lie within the plane, that means that all the torques generated by those forces are going to point either into or out of the plane. And so our vector addition problem is really just a one-dimensional vector addition problem where we're going to be adding up the z components of the torques from each individual force. So as an example, let's look at our long thin rod again. So there's 6 forces acting on the rod pivots about its center point. 5 of these forces have the same magnitude. So forces 1, 2, 3, 5, and 6 are all 100 newtons in terms of their magnitude. Force 4, it's going to be half as much. So force 4 has a magnitude of 50 newtons. We'll let the rod have a length of 1 meter. We'll let the angle that force 5 makes with the rod be 30 degrees. And so we've set it up so that force 1 acts at the pivot, force 2 acts halfway from the pivot to the end of the rod, and then forces 3, 4, 5, and 6 all act at endpoints of the rod. So to start with, we need to pick a coordinate system. So just like with any vector addition problem, I need to know what my coordinate system is so I can correctly calculate the components, so I can add those components up in my component equation. Let's let positive z point out of the page here. And then what I'm going to do for each of these forces is I'm going to make a simple diagram showing me R and F, so the vector that runs from the pivot to where the force acts and then the force. That's going to let me figure out what the angle is between those two vectors. I'm then going to use my geometric way to calculate the magnitude, and then I'll use my right-hand rule to figure out what the direction is. So let's start with force 1. Force 1 acts at the pivot. So the R vector for this one is the 0 vector, which means the magnitude of the torque generated by force 1 is 0. Right? Any force that acts at the pivot generates no torque. That means I don't have to worry about direction. Force 2, the position vector points to the right, the force points down, the angle between those is 90 degrees because I know that for forces 1, 2, 3, and 4, they're all acting perpendicular to the rod. Again, now that I know what that angle phi is between my two vectors, I can use my geometric approach to calculate what the magnitude of the torque is. And so the magnitude of the force, magnitude of the position vector, sine of the angle between them. And so in this case, that's 100 times 0.25 times the sine of 90. And so that's 25 Newton meters for the torque generated by force 2. Again, my right-hand rule says, point your thumb in the direction of R, your fingers in the direction of the force, your palm pushes in. Right? That's one way to think about the right-hand rule. The important detail is that I get the torque generated by force 2 points into the page, and given my choice of out of the page is the positive direction, that means when I plug this, that means that the z component for this torque is negative. Let's deal with force 3. So again, I'm going to start with my diagram. R3 points to the right, force 3 still points down. Again, it acts perpendicular to the rod, so the angle between the position vector and the force vector is 90 degrees. I can calculate out the magnitude. So again, I'll do magnitude of the force times magnitude of the position vector times the sine of the angle between them. In this case, because the length of R is half the length of the rod rather than a fourth the length of the rod, that's 50 centimeters rather than 25 centimeters, which means I'm plugging in 0.5 for that length rather than 0.25 like I was for the torque generated by force 2. And so I get that, or the torque generated by force 3 is 50 Newton meters. So by moving twice as far away, I get twice as large a torque. Again, the direction works out being the same. So my right-hand rule tells me that the direction of the torque generated by force 3 points into the page. So again, that component, the z component, given my choice of coordinate system, is going to have a negative sign. Force 4. Well, now force 4 acts on the left end of the rod. So for starters, the position vector flips around. It now points to the left. Again, force 4 acts perpendicular to the rod, so the angle between those two vectors is still 90 degrees. can calculate the magnitude of the force, length of the position vector, sine of the angle between them. So the magnitude of that force here, I'm told it's 50 newtons for force 4. Again, the length is still half the length of the rod, that's 50 centimeters. Convert that into meters, 0.5 meters. Sine 90 is still 1, so I get the magnitude of the torque generated by force 4 is 25 newton meters. My right hand rule now says, well, if you point your thumb in the direction of R, your fingers in the direction of F, your palm is now pushing out, which means that the Z component given my choice of coordinate system for torque 4 needs a positive sign. Force 5. Well, of course, force 5 is the one that's not acting perpendicular to the rod, but I want to draw it in or draw the position vector in, and so what I notice is that the angle between those two when I draw them from the same point is 30 degrees. So here the phi in my sine term that I'm going to use to calculate the magnitude is theta. I go calculate that magnitude. So again, magnitude of the force is 100 newtons, acts at the end of the rod, so that position vector has a length of 0.5 meters. Now I want the sine of 30 degrees, and so this is 25 newton meters. Again, using my right hand rule here, what I get is that the torque generated by force 5 points into the page again, and so this torque needs a negative sign in terms of its component given my choice of positive Z pointing out. Force 6. Well, here what I notice is that the position vector and the force lie along the same line. So again, the angle between them is 180 degrees. When I go to calculate out the magnitude, one way to think about it is, well, I know the sine of 180 degrees is 0. Therefore, the torque generated by force 6 must be 0. Another way to think about it, of course, is that force 6 acts through the pivot, right? So its line of action runs through the pivot, which again means there's no moment arm, so therefore it creates no torque. No torque, I don't have to worry about direction. So now I can come back, and now that I know each of the components for all 6 of these torque vectors, I can add them up. So my equation for calculating the net torque is very simple. I want the Z component, so the component equations just add together the Z components of all 6 torques. Again, if I want to, I can create a very simple table that's mapped to my equation. Here I'm plugging in, so the net torque, its Z component is what I don't know. I have gone through and calculated the individual torques from all 6 forces. I've got the right signs based on what my right hand rule told me. And so again, now I can just plug those into my equation, add them up, and when I do that, I get the Z component of the net torque is negative 75 newton meters. And so what that means is the net torque here has a magnitude of 75 newton meters, and it points in the negative direction. So the component's negative, meaning that the net torque points into the page. So at the end of the day, when all of these forces act, they're acting to make the rod spin clockwise about that pivot.